Hello everybody. In this video we are going to continue the discussion on projectile motion and take a look at a couple of examples immediately afterwards. Up until this point in the conversation, we've introduced the notion of projectile motion. We've talked about the fact that essentially what we're doing is we're trying to mathematically model and discuss what occurs when you take a particular object, say centered at the, in this case, the origin of the xy plane, and you give it some sort of initial velocity and you launch it into the air. The baseline assumptions that we have inside this context is that there are no forces at play, like wind or anything like that, and that the only force that we have to consider is that of Earth's gravitational force. With the setup that we've developed here, the initial conditions we considered were an initial position, which for simplicity's sake at the current moment we're going to assume the initial position r0 is occurring at the 0 vector. And we assume that our object is being given an initial velocity we'll call v0, and if you let alpha be known as, say, the firing angle, it is the angle of elevation that the initial velocity makes with the horizontal axis, then the horizontal and vertical components can be computed as such using a little bit of trigonometry. From that point forward, we introduced Newton's second law of motion, which allowed us to write down the forces that are acting upon the object that's being projected into the air. We observed that mass times acceleration, given in the context of our vector function for position, can be written as m times the second derivative of r. Where then we talked about how in our situation Earth's gravity is the only force that's at play, and Earth's gravitational force acting upon this object results in a downward facing force whose vector can be modeled with 0 as its x coordinate and negative mg, where m here is the mass of the object we're considering, and g here is the acceleration due to Earth's gravity, which, for all intents and purposes, we're going to take that to be 9.8 meters per second squared. The negative here is what helps us force the gravitational vector to point downward. And therefore, if we're focusing on this object that's being projected in the air, the forces acting upon it, which we have up here, are equal to the force of gravity acting upon it, which is this vector. And if we equate those two vectors and cancel out the mass of the object, because that's the same constant, then we get this equation. This equation on the left is the derivative of an object, and on the right is some sort of a vector function. And so what we're going to try to do now is we're going to try to find a position vector r, which, given here in purple, models the exact position of the ball at any given moment in time. We're going to try to get that position vector r while only knowing information about its second derivative. So of course we're going to have to undo the derivative, and that process involves integration. Now the process we're about to do is we're going to engage in something that's known as solving a differential equation. And so using the notation that we have in the book, we have here the following differential equation. It's exactly what we have above, that r double prime of t is equal to this vector 0, negative g. This is called a differential equation because it's an equation for which we're trying to solve only knowing information about the derivative of our function. If you go on to take a class called differential equations, otherwise known as diffie-Qs, because of the first few letters in each of these words, you'll learn how to solve a great many additional differential equations. But this one is a fairly simple one to work with here. Now, what we're going to find is when we integrate this, it's going to spit out constants. And we have to be able to figure out exactly what those constants are. And it turns out that those constants can be solved for through use of what are known as initial conditions. And so the initial conditions for us is the following. We have that our initial position, which was r naught, is equal to the 0 vector. And we know that our initial velocity is equal to v naught. So these two pieces of information will help us solve for our integrating constants as we integrate this differential equation. So, as we do that, let's observe the following. If we integrate once, our goal is to get the first derivative, because the first derivative, using the second fundamental theorem of calculus, is equal to the integral of the second derivative. But of course, the integral of the second derivative is the same as the integral of the equation that we have, which is the vector 0, negative g, where this integral is taken dt. And through our understanding of integration component-wise, we know this is going to be equal to the vector of the integral of 0 dt and the integral of negative g dt. Now, when I integrate 0 here, the integral of 0 is just a constant. And when I integrate negative g, since g here is the acceleration due to Earth's gravity, this is just a constant. And so this will integrate into just the constant times t. So if we wanted to be very, very pedantic about this, we could write this as now a vector where we might have some constant a. And then for the second component, we might have negative gt plus b, for example, where we'll note here that a and b, these two are constants. So the things I just highlighted, these things are constants. But we don't really want to have to write constants for every single integral, and we don't have to, because we could always rewrite this as the vector 0, negative gt, plus the vector containing the constants. You'll verify by vector addition that this vector we had here is exactly equal to this vector. So if instead we were to rewrite this overall vector here as a vector of constants, we could rewrite this overall integral as the vector 0, negative gt plus c, we'll call it c1 because this is the first time we've integrated, and we see that exactly this is a vector of constants given by a, b. We don't know right now what that c value is equal to, and if we don't have additional information, we might not be able to find it. However, because we know something about the derivative of position, notably the derivative of position is velocity, this c1 can be solved for. So observe that if we, for example, take r prime and evaluate it at 0, on one hand, we're going to get, if I plug in 0 to this vector equation right here, we're going to get 0, negative g times 0 plus c1, because that's a constant, which of course is just the 0 vector, plus c1, which of course is just c1. So if I evaluate this equality for r prime at 0, I'm getting just c1. But we also know that r prime of 0, that's literally the initial velocity. That's the same as what we had up here. That's r prime of 0. But so what we have is that since v naught is the assumed initial velocity, what we have is that r prime of t now is given by the vector 0, negative gt. However, this constant c is now equal to v naught, which is one of our initial conditions. V naught is an assumed item we had at the beginning of the entire conversation. So what that means is we've started with the second derivative, we've integrated it once, we used one of our initial conditions to solve for the constant, and now we have the first derivative. So we took, for example, some notion of acceleration, and we've yielded velocity. We can do the exact same process to start with r prime and somehow get back r. So we're going to do the exact same thing. R of t is going to be given as the integral of r prime of t, which we know now is the integral of the vector 0, negative gt plus v naught. Now there's a couple ways to visualize what we're about to do. You could apply this integral to the first vector and then add it to applying it to the second vector. And if we do that, we might get something like this. The integral of the vector containing the integral of 0 dt times the integral of negative gt dt plus the integral of v naught dt. And we have to again play this constant game. But here it's a little bit more complicated because notice that when we integrate this vector over here, v naught, each of those individual components are constants. Well, maybe instead of going through, let's go ahead and barehandedly write this out. This is going to turn into, let's see, the integral of 0 is going to be another constant. So let's go with C this time. The integral of this object here, taken with respect to t, is going to be negative 1/2 gt squared plus a constant. Let's call it d. Plus, what happens here? Well, remember, v naught has its own components. We know that up here. But each of these are just numbers. So at the end of the day, this integral turns out to be literally the vector containing the integral of the first constant, which is just the magnitude times the cosine of the firing angle, dt, and then the integral of the second component, which is the magnitude again of v naught, along with the sine of the firing angle, dt. But you'll notice that each of these are dt integrals, and as I keep mentioning, the components for v naught are just constants. This is an initial vector. This is not a function. So if I integrate a constant, there's no t's in here. If I integrate a constant with respect to t, what I'm going to get is, just like when I integrated all the way up here, when I integrated this g and it just spit out a t and a constant, each of these are going to get a t and their own constant. So what that means is if I steal this line, what I'm going to get at the end of the day is that the integral symbols will go away. I will get a t plus its own constant, I don't know, call it e. I'll get this with a t plus its own constant, call it f. And what we see now is that this c, this d, this e, and this f, these are all just constants. We can again, in the same way we did up here, we can pull them all out as one giant vector of constants. And as a result, this is simply going to turn into the vector 0, negative 1/2 gt squared plus what we're going to end up with here is just, this is v naught just with a little t attached to it. So this is going to be v naught with a t plus some constant vector. Let's call it c2, where c2 is made up of those constants c, d, e, and f. However, now we need to figure out what that C2 is. So we're going to do exactly the same trick. We're going to observe that R of 0 is equal to, if I plug it into this final answer here, we'll again get a 0 here, so that'll be the 0 vector. We'll get V naught times 0, which is again 0. So here we'll only get C2. But since our initial position here was assumed to be 0, but since R0 is equal to the 0 vector, we have that C2 is equal to the 0 vector. So what that means is that R of t is not equal to this entire thing with an arbitrary C2, but it turns out that C2 is 0. So what that means is that R of t is equal to exactly this vector up here, right there, which, if we were to expand V naught in terms of its first and second components, and then combine these two vectors together, we'll get this representation. Where there is a typo here, I should note, there should be a t right here. But essentially what we have is that the position of our projectile that's been thrown in the air is equal to, in the first component, this quantity, and in the second component, this quantity. This is notably more challenging than what we saw in pre-calc or calc 1, but it really does encode all the information we want. We have time, t, we have an initial velocity, we have an initial firing angle, and we have Earth's gravitational acceleration. This object is known as the vector equation for the path of an ideal projectile motion, meaning that there's no wind or anything like that. As I've been using the words, I'll formally write it down. The angle alpha is the launch angle, firing angle, or the angle of elevation, and the norm of V naught is, of course, speed. This is the projectile's initial speed. These are all things we can solve for if we'd like. So let's use this equation to do a quick example. Here we have that a projectile is fired from the origin over a horizontal ground, and the initial speed is 500 meters per second, and the launch angle is 60 degrees. And the question is, where will the projectile be 10 seconds later? So I'm going to start here by drawing a picture and collecting some data. So what we have here is that an object is starting at the origin, it's being fired upward, and it comes down and hits. And apparently it has an initial speed, which means if this is our velocity vector that we're starting with, what we have is that the magnitude of V naught is 500 meters per second. And if this is our launch angle, we have that that's equal to 60 degrees. And the question that we're trying to answer is, where will the projectile be in 10 seconds? That answer is given by wherever R of t is, where t is taken to be 10. That's what we're looking for. This is the position of our projectile in 10 seconds. Fortunately, however, our initial position is still here at 0, 0. We have a firing angle, and we have an initial speed. So if all we want to know is R of 10, this equation encodes all the information we're looking for. So we find that R at 10 is equal to the vector, well, it's going to be V naught times cosine of the firing angle times t. That's the first coordinate. And the second coordinate is the speed times the sine of the firing angle minus 1/2 Earth's gravitational acceleration constant times t squared, where here we want t to be equal to 10. So if we evaluate these objects, what are we going to get? We're going to get, this is 500, cosine of 60 degrees is going to be 1/2, t is equal to 10, the speed again here is 500, the sine of 60 is square root of 3/2, minus 1/2 times g, which we know is 9.8, times 10 squared, which is 100. And then if you go ahead and compute these further, you can verify that you're going to get the vector whose horizontal component is given by about 2500. Obviously, this is going to be an approximation because of all these decimals that we have here. So 2500, 3840. So in words, the projectile after 10 seconds is 3,840 meters in the air and 2,500 meters away. So this is where we can use this complicated formula to actually find some interesting information. What remains is a couple of observations and some important takeaways. For one, you are more than welcome to have the following objection. In Calc 1 and Calc 1 and Pre-Calc, every time we talked about a projectile, it was always about talking about parabolas. And you say, well, parabolas, aren't they supposed to be some function of x squared, question mark? And why does this not look like that? Well, it turns out the answer is actually yes, this is a parabola. Because if I come back up here to this equation right here, if I make it my goal to take this parametric equation and eliminate the parameter, that would amount to taking x equals this first component and solving for t. And once I do that, I want to substitute that into the second component. If I do that, t is going to be equal to x over this quantity. And when I plug that in here, we'll get sine over cosine, that's a tangent, and then we'll get some cosine squares here. And if you do that, you can reduce this equation into the following form, where we have y equals negative of this constant times x squared, plus tangent of alpha, this constant, times x, and this is exactly your favorite parabola that starts, that has, observe, if I plug in x equals 0, I have an x-intercept, so I know I have x equals 0. There's some other x-intercept here, because it's a parabola. It's negative in its leading coefficient, so I know it faces down. And so I know that this is the path of the projectile. This is how we would have given it to you in Pre-Calc or Calc 1, where we wouldn't have given you what the constant in front or this second coefficient, what those actually are. We just kind of give you numbers and say, go. Here, we actually have built the machinery to give you an explicit representation for what those constants look like. Interestingly, of course, it's all dependent on this Earth's gravitational acceleration constant. If you were on a different planet or a different mass with a slightly different acceleration constant, you can do all the same computations. All of these things are true even if you're not on Earth. You just have to change what your constant is. So this really is a more generalized type theory. So with this framework, though, you might recall questions that we would have asked in Pre-Calc, for example. What's this point? Clearly, this is the point where the object comes back down and hits the ground again. And sometimes, depending on what book you might have used or what your teacher might have said, this distance is sometimes referred to as the range of the projectile, because that's how far it went. Of course, when you found the vertex of the parabola, this, the y-coordinate of the vertex here, this is the max height of the object. And you would have computed that by finding the y component of where this was maximized. In Calc 1, you would have answered that question by finding the y-coordinate of when the first derivative was 0. But the question is, all these same things, do they exist in the context of this more realistic model situation? And the answer is yes. So if we want to determine when the projectile's maximum height occurs, we might observe that sort of what we're talking about up here, this is going to occur exactly when the first derivative of the position is equal to 0. This is the position function, and so we want to look at when its derivative is 0. But the derivative of position is velocity. So in some sense, the correct way to phrase this is the projectile's maximum height is going to occur when the vertical component of its velocity is 0. Because going up, the vertical component of the velocity is positive, 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 positive. And then at a certain part, the vertical component of the velocity starts to hit negative again as it comes back down. So the way I like to think of that is we want to take the vertical component of the position vector, and all I did was steal that exactly from the formula that we developed up here. And I'd like to find the t value for which this vertical component hits 0 after we differentiate it. So this is going to occur when the magnitude of v naught times sine of alpha minus now gt is equal to 0. Notice that, by the way, I started with the position and differentiated it to get velocity. You could have just come up to our computation and stolen the actual velocity vector here. And if you look at the vertical component of that, which is negative gt plus the vertical component of v naught, that would be exactly what we're considering right here. And so we're setting that vertical component of its velocity to 0. And if we solve that equation, what we're going to get is that t here is going to be equal to the magnitude of the initial velocity v naught times sine of the firing angle over g. But this, of course, is not the actual maximum height. This is simply the parameter t for which the maximum height is going to occur. So the maximum height is at, well, it's going to be the y-coordinate of the position vector. That's this thing right here. It's going to be the y-coordinate of this, but evaluated at this parameter. So what are we going to get there? We're going to end up with is going to be at the magnitude of v naught times the sine of alpha multiplied by this t value, minus 1/2 times g times, again, the same t value right here, squared. So let's look at this real quick and see what this turns into. You'll notice, for example, these two g's, well, there's going to be two g's over here, so one of those are going to cancel with that g, leaving one g in the denominator. We have a g in the denominator over here, so these do have a common denominator. Up here we have a square of v naught, it's the magnitude of v naught and sine. Here we also have the square of the magnitude of v naught and sine. So really what we have here is the exact same things. So it's like having a whole minus a half of itself. The result, of course, is going to be just like if you have a whole pizza and take away half of it, what do you have left? You have half the pizza. So what we're going to have here is we're going to have the magnitude of v naught times sine of the firing angle squared all over g, but we want half of that. So we'll divide this by 1/2, and that'll be our maximum height. So the answer to the question of what is the projectile's maximum height, that occurs at this t value for which the maximum height is actually this high off the ground. Another common question that gets asked is, what is the total flight time? How long does this object stay in the air? Well, we want to figure out when the object hits the ground, and when it hits that ground, we want to figure out what that t value is. Because the t value is always going to start at 0, and so whatever that t value is when we hit the ground, that's how long the object spent in the air. Well, this of course is going to occur when the vertical component of its position is 0. The vertical component of its position, as we saw up here, is exactly this component, and if we set that equal to 0, we can solve. Now, if we do that, what we see by factoring, please do not, by the way, move this to one side and cancel a t. You can't cancel the t unless you know the t is non-zero. The correct way to do this is to factor a t out. We'll get t times the magnitude of the initial velocity times sine of the firing angle minus 1/2 gt is equal to 0. And this gives rise to two equations. One, that the first factor is equal to 0, and two, that the second factor is equal to 0. If the first factor is equal to 0, we get t equals 0. The second factor, however, will be the magnitude of v0 sine of the firing angle minus 1/2 gt is equal to 0. And now we can observe that t equals 0 is where we started, and then as we fire and we come back down here, once we come back down here and hit the ground, that'll occur at the other t value. So it turns out that for the question of what the total flight time is, the answer is going to be whatever the solution is to this equation. So that tells me that the total flight time is t equals, solving this equation, we'll end up with 2 times the magnitude of v0 times sine of the firing angle over g. And that becomes the answer that we're looking for. That's going to be that how long this object spends in the air. The last thing we'll take a look at here is the range of the projectile. That's exactly this horizontal distance. But we just came up with the hang time. That's the time that it takes before we hit the ground again. So we know when the object started, and this object usually starts at 0, and we know how much time it takes before it hits the ground again. All we have to do is figure out what the horizontal position is at that terminal time. And so the range, which we'll sometimes denote as capital R, is the total distance traveled, and we can find it by evaluating the position vector's horizontal component at this value. So the range is going to be equal to the horizontal component, which if we come up here, we'll remind ourselves that this was the horizontal component. And so what we're going to do is we're going to take the horizontal component, which is, just saw it, and then magnitude of v0 cosine times t. So this is the magnitude of v0 times cosine of the firing angle times t. And we're going to evaluate that at t equals exactly this quantity. And this is going to give us somewhat of a large object here. What are we going to get? We're going to get, let's see, we're going to get the magnitude of v0 squared. We're going to get a 2. We're going to get a sine of alpha and a cosine of alpha. And then we're going to get all that over g. And now, I've referenced this earlier in this semester so far, but Based on our experience with trigonometry, this object right here is actually a well-known trig identity. So that is the trig identity for, if I rewrite everything else, that is actually the trig identity for sine of 2 alpha. So that is a trig identity that we can utilize. And so this becomes the range. Overall, if you take a look at, for example, our book, but pretty much any book that does anything on this, they'll just straight up say, okay, the maximum height occurs here, this is the height. Total flight time, boom. Range, boom. But you really should know how these things are coming to be, because that's the relevant information that we need to take out of this. The final thing we'll take a look at here is the following. If we look back at our original picture that we drew way up here, we assumed that our initial position R0 was fixed at the origin 0, 0. In reality, this doesn't have to be true. For example, if you're firing a cannon from atop some sort of rampart or something, then clearly you're not starting at 0, 0, you're starting way up here and then firing the object. And so you might be interested in moving your starting location to some other XY coordinate. And the question is, how does that change this entire game? Well, it actually doesn't change it that much. Essentially, what's going to happen is you're going to take this original position vector that you find, and in the X and the Y coordinate, we simply need to add in those respective initial conditions. Because at the end of the day, the only place we used this R0 was at the very end, right here, and all we did was add that constant to our proposed position vector. And when we add in a new xy vector, all it's going to do is add to the respective components. So what that means is we can say that if our initial position is given by some other vector, like x0, y0, meaning, for example, that we're starting up here, say, at x0, y0, then we fire our object. We still have all the same things because vectors don't care where you start. We still have the same vector being initially applied. Now, though, we sort of have these imaginary axes here that we're dropping the perpendicular down to. But those are still just the vertical and horizontal components of this initial vector, v0. So really the only thing that's changing is we're taking our position vector and we're adding an x0 and a y0 to it. And everything else is basically running the same. And so our position vector, if we just tack on the x0 and the y0 to the respective coordinates, it literally solves the entire problem. And so this is a very convenient and easy way of integrating a change in initial position, and it's really only granted to us through use of our vector formulation. Now I will say, if your initial vector changes even a little bit, these formulas right here, and right here won't work as is. So I really do urge you, you need to learn the sort of the process for how we do this, because the process will remain the same for each of these. And if you change your initial position and apply the process to your position vector, then you'll always get the right answer. But that's about it. That's all I wanted to say on projectile motion here. There are some problems you can take a look at in the book, and I really encourage you to do so. And as you work through all of that, if you have any questions, of course, feel free to reach out. I'm more than happy to help. But otherwise, I'll catch you all later.